Hello, we are team FTC 23849.4. We are from Washington, located in Bellevue. And this is our story about building a compact robot and showing you guys how you can build one as well.
Okay, so today we're going to cover why should you even care about building a compact robot, the advantages and disadvantages of building a compact robot, how to design compact robots, and the challenges that come when you actually have to design the robot itself. And we're also going to cover, is it worth it, and who is it for?
Yeah, so that's one slide too far. Two slides. All right. So why should you care about compact robots? Well, firstly, depending on each game, you will have obstacles. For example, back in Fight Frenzy, if you remember, you had those terrain. They were really annoying, and they took time to navigate over. However, there was a 13-inch gap between the terrain and the wall. Most of the teams who performed really well at Worlds, and UAC as well, had a very skinny bot that was able to go through that channel and score and cycle really quickly. Furthermore, back in center stage, you may have remembered designing that robot that was under 14 inches. That was obviously a struggle, and also shorter, less wide ball would also cross the trusses more easily. So, by designing a compact bot, you can navigate these game obstacles.
So additionally, if you have such a really compact robot, you can pull off maneuvers like this, where if a bigger robot is playing defense on you, then you can squeeze in through the gaps and prevent them from actually limiting you from scoring. And also, these smaller robots are lighter, and they have better agility, so you can easily get around bigger robots.
And additionally, a more compact robot can also extend your game abilities. For example, in this year, you have this 42-inch extension limit. By having a compact bot, you have less of the robot outside of the submersible and more of the robot inside of the submersible. This allows you to extend further into the submersible, which extends your capabilities in selecting your samples. This gives you that extra performance that you might need, and you see this across all of the really good teams who competed at Worlds. Each of the robots were very compact, and that extended their performance and helped them gain an edge over other FTC teams.
So here are the disadvantages of building a compact robot. So CAD and planning is mandatory because there's a lot of stuff that is packaged in these robots. So you can't really free build a robot like this, because you can see these motors are really close together, and there's a lot of stuff you have to play with tolerances a lot. So CAD is gonna be a requirement. And also space in these robots is limited, so you're really gonna have to think a lot about where you want to place your mechanisms, because if you fill up too much of your robot with one thing, you're not gonna have space for another. And coming with space limited is like you're gonna have poor accessibility. That depends on how you design your robot, but generally, if you have a smaller robot, accessing different parts could be more difficult. And there are also going to be a few design challenges when you design the robot, as I stated earlier. And then small robots also limit iteration, because as you can see, there's not really any space on this robot to add anything. Say if you wanted to add like a servo to push samples or something, there's not really any space left on this robot to do that. So you would really need to get your design right the first time if you want to design a compact robot.
And also, it does take a lot of time between CAD, planning, and designing and making sure everything fits together. This is a huge time investment. And also, just by being compact does not guarantee you success. It can be part to being key to your eventual success, but it does not guarantee it. So, how do you actually design a compact robot?
So one of the most important things when designing a compact robot is your center of gravity, because smaller robots have a much smaller surface area contacting the ground, so they are more prone to tipping over if they don't have a correctly placed center of gravity. So in order to get a good center of gravity, you should strategically place heavy parts low to the ground. So for example, this robot, when I was doing the CAD, I intentionally tried to place all the motors down here at the bottom, so, and then I used different mechanisms to transfer the power up to different places. So over here for the intake motor, I used a belt over here, and then for the outtake we have GT2 belts over here to transfer the power to the spool shaft in between the drive motors. And then also, when you're designing a compact robot, you want to select good mechanisms. So for example, if you're using a double reverse 4-bar, it's probably not a very good idea for a compact robot because they can get quite bulky. And so you want to choose a balance between bulky and not bulky. And then also accessibility. Accessibility is extremely important when you design a robot, because if you can't access stuff or remove stuff for quick changes or replacing, you're gonna have a lot of issues during competitions when stuff breaks. So, for example, on this robot, this is an access hole for our outtake spool shaft, because we were having a lot of issues with our outtake spools, so we've been adjusting that, and they've really been saving us these past few days. And then also you want to consider whether you want to use custom parts or COTS. So you have to find the right balance, because COTS are really useful because they're pre-manufactured. You know they're gonna work, but the thing is they can get quite bulky if you only use COTS. So you do want to keep a balance between COTS and custom, because in custom you have a lot more freedom. You can design things to be a lot more compact.
Okay, so now in the CAD, after you brainstorm off your designs, you're going to want to go into CAD. Now, CAD does have a lot of different stages, but one of the most important stages is going to be your master sketch. Your master sketch is essentially just an entire 2D representation of your whole robot. And this allows you to follow a top-down CAD workflow where you start from the overall layout of the robot and then really get down to the nitty-gritty details. So why is this so important? Well, it is a centralized, easy to edit place for you to adjust the features of your robot. You can constantly adjust it, which means that if you're designing a custom compact robot, you might need to be repositioning your mechanisms over and over again so that you can get that right amount of compactness and placing things together perfectly. That really helps you optimize it for space. Now, master sketching is an advanced technique. You need good spatial reasoning skills. You need to be able to interpret a 2D sketch into a 3D object. And you also need a comprehensive knowledge of FTC parts so that you know what kind of mechanisms you need to design and how big they will likely be. You also need to know the general layout of an FTC robot, the most important parts, and many other things. Now, to get started on this, you can follow some learning resources. For example, Seattle Solvers on their YouTube channel, they do have a video that kind of details their process for creating their master sketches.
So the challenges with building a compact robot. So we've already covered accessibility. It's really important that you have accessibility, or you are going to have issues when you try to replace stuff in your robot. And then there is going to be challenge when you try to design your robot. It's going to be pretty difficult, and there are going to be a lot of limitations and trade-offs. And there's also little room for expansion, and there's not very much flexibility in such a compact robot. So to like iterate on a robot, you might have to redesign. And then also your mechanisms will get tightly crowded inside a compact robot.
So at the center of this leads to the biggest challenge of them all, which is wiring. So if the slide will move. So how will you wire this extension? You have very little room and you need to extend a lot of space. Well, there are various ways where you can design, you can manage cables for extension mechanisms.
So one easy way to manage cables are cable chains. So basically there's this plastic chain and the wires will fit inside it, and the wires are going to be completely contained inside it, so it's really safe for your wires. And also the cable chain is really controlled because it only moves in one plane, so unlike a loose wire, it won't be able to move side to side. And it's also really reliable because a lot of teams use it in FTC. However, it is limited by its extension, so and it can also be bulky depending on how long it is and how close it is in the retraction stage.
Now, a good alternative can be a scissor chain. These scissor chains, they can offer a lot more extension. For how long they are or how big they are, they can provide extension up to triple or quintuple how much they actually are in size. They're also thin and predictable. However, they can get heavy, and if you do use plastics for your linkages, they are prone to breaking.
So what we did on our robot was we used these cable coils. So they're very versatile because you can use them virtually anywhere. So we've only used cable coils on this robot for both the intake and the outtake, and it's been working well for us so far. And they also can provide a good amount of extension depending on how much it is retracted. However, it does require custom wires and coiling. So this is a backup coil we made. We had to coil it ourselves, but there are websites that do sell pre-coiled wires, but they are a lot more springy and they will require a lot more torque to extend. So that mainly depends on how much torque your extension motors do have. And also they might require soldering or special connectors. So we didn't go for soldering because because under high stress and lots of motion it can't disconnect. So we opted for these connectors here, which basically they cut into the wire and then they can connect two ends, and then we just connected these cut servo extensions into the servos. So that's how we use this.
Now, alternative to this can be loose cables. There's less setup that is needed, and it's workable in a pinch. However, it is more uncontrolled. It can get snagged in other robots. It can be unreliable, and if you do get to be reliable, it's very difficult to do. Now, RK did a great job of it. And also some more tips with cable management. In a compact robot, you really do not have a lot of room. You can't really afford to have a lot of loose wires. So this means you might need to cut your wires to length. So a good way to do this is by using Wago connectors. These connectors are great and they're reliable. You can cut them to pieces. You can cut wires to the set lengths, such as your motor wires, so you can really avoid the jumble and mess of wires. Now you should also be following standard wiring practices, such as using zip ties to guide the wires away from any moving mechanism, and also using stress reliefs so that you don't really get any pulling forces by your connectors.
So some advice for building these compact robots. You should watch a lot of Behind the Bots. They're really useful, and most of the really good robots on Behind the Bot are really compact. So you should try to reverse engineer them and take inspiration from them, and learn and improve your design as you build it. And it's really important to note that it's easier to iterate than to create. So basically you have to realize that your robot isn't going to be perfect the first time you make it, but it can become really good if you keep iterating on your robot.
And if you really want to get it to be really compact, you can do rebuilds, but just make sure that you don't do them too late. Now, there are some additional advice. So, set limits to how small you make your robot. Sometimes it's worth sacrificing a few millimeters for that extra accessibility or less complexity. You really do not want to over-engineer these complex robots. You want to really design for reliability, because fixes can often be difficult in these. You also want to plan out and visualize potential wire routes and anticipate where moving parts may be and how you may avoid them with your robots. Alright, that's our presentation. Thank you.
Can you demonstrate each action that the robot can perform, like picking samples, how it would play specimens?
So basically, I don't have the controllers right now, but so for picking up, it would just come out like this. It'll pick up, it can move side to side. It'll pick up and then it'll turn back in for the transfer. And then we have an option to side deposit for specimens, so it can side deposit here to the human player, so we don't have to turn. On both sides, you can side deposit. And then for the transfer, it'll come in like this, and the arm will be over here. And then we have an auto transfer, so this will grab on, this will release, And then for samples, we'll go all the way up and then turn the arm like this. And then in auto, we have the option to use the side game. So basically, we don't have to turn the robot, and the heading will get messed up less easily because of that. And then for specimens, we would pick up from the wall like this, and we have a spec aligner here to help the driver. But we'll pick up from the wall like this, and then it would go up. And then depending on which chamber we're scoring on, it'll rotate to that side.
So for the cable coil, how many wires that can there are, and how many servos that you are connecting to?
So each servo needs 3 wires, the ground, the power, and the signal. So basically, you need to multiply your servos by 3, and that's how many wires you'll need inside. So basically, you'll search. So for servos, they need to be 22 AWG. That's the thickness of the wires. So basically, you can go on Amazon, or there are the special coil making people that I mentioned. But you would search up 22 AWG, and then depending on how many wires you need inside, like this one is a 12 core, I think. So do like 22 AWG 12 core wire, and then basically these showed up. And then the way we made them was we used a tube, and then we tightly wrapped this around the tube, and then we used a heat gun to make the wire set in this position. Yeah.
What's your odometry setup, and also do you have a vision system in place?
So for odometry, we just have 2-wheel odometry with pinpoint. It's right here, and then the pinpoint is on top of the battery. We didn't have time to make a vision system because we built the robot in like a week, so yeah.
Alright.
Yeah.
How did you mount your batteries?
So in the drivetrain, it's a normal parallel plate. So we have this metal piece over here, which sticks out using standoffs. So then that's how the motors for the drivetrain are mounted. Inside, we have the secondary inner plate for the intake, because our intake sides are mounted on the innermost part of the robot. So the intake motor is mounted on that secondary inner plate over here. And then these are the bare motors for the outtake. So what we did was we made these plates which connect to the back of the robot here. They connect here. And then we also have 2 standoffs on the top of the robot.
Can you release the cap for it?
Unpublicized it
Oh my god.
because they're unfinished. But we have standoffs over here and here to support the plate.
So how much does your robot weigh total?
30 pounds.
27.
27 pounds.
27 pounds.
It's been running around a lot. Lost some pounds.
And what's your opinion on using badge retractors for wire?
So we have used them in the past 2 years. The thing I don't like about badge retractors is that it's a loose cable wiring system. So loose cable can get stuck everywhere, and like especially in this robot, like there's not really any space for a loose cable because it's just so compact. I mean, I guess you could put it on the side here, but it would get really bulky. Yeah.
You're using the plexiglass near your drivetrain to protect side things going in? I mean, I think it's the first robot I've seen that has plexiglass around that space.
Yeah, so this is, it serves multiple purposes. So the main purpose is to protect this wiring, because if this wasn't here, this wiring would all stick out, and then,
It goes down to the back base, right?
yeah, so
What's the purpose for it?
mainly to just protect the drivetrain from impacts. And also it was to aid in mounting, so it was because we didn't want to put too many screws on the control hub, because if it hits here, we don't want the force to go into the control.
Providing support for the piece
Yeah.
on top, right? So it's not flimsy. Okay, got it.
Yeah.
Can you talk some about your strategy or process for planning wiring in the robot?
Yeah, so basically we started planning wiring from the very start of the CAD. So every mechanism I made sure that we had a wiring plan in place. So over here I made sure that I made 2 holes for wiring over here. So the wires could pass through, and then in the inner plates I had 2 specific wiring holes here. And the reason I made specific wiring holes instead of using pockets was that the pockets are not designed around the wiring, they're designed around weight reduction. So if the pocket is in the wrong spot, the wires might interfere with some other mechanism. So that's why I made the wiring holes beforehand. And then mostly the wiring plan, we just tried to do the wiring plan directly from the start. So, yeah.
What auto-pathing software are you using?
We're using Roadrunner.
And that, and you're interfacing that with the Limelight and it works just fine.
But we don't have a vision system.
Or, not Limelight, I mean the pinpoint, sorry.
Yeah, we haven't had any problems yet. I did run into some issues with the localizer, but I debugged them myself. I still don't understand really what went wrong, but I was able to fix it. Yeah.
What's your ground clearance?
It's designed to have 7 millimeters of ground clearance, but on the field it becomes more like 3 millimeters. Yeah.
How are you extending and retracting the linear slides at the front? Is that just a string?
Yeah, it's just a string here. The spools are in the back over here.
Okay.
Other questions?
Alright, cool. Thank you for coming.
Yes.